Thank you. So I'm going to talk about the Poincare-Bendixson theorem that we formalized in Isabelle HOL. And this is joint work with Fabian Imler at CMU. Okay, so, so here's a quick outline of my talk. So I'll tell you the background you need to know about the theorem. I'll tell you the theorem itself. But actually for this talk, I won't be talking about the proof of the theorem. I'll be going in depth into the proof of the theorem itself. I want to focus instead on kind of what makes this theorem interesting to formalize. Okay, so in particular, I'll be focusing in on one particular lemma that's used in the proof that is, that showcases these challenges. Okay, and then I'll end with some remarks. Okay, so let me get started with the background. So I hope everyone here has some passing familiarity with differential equations, in particular ordinary differential equations. They are very useful all across the sciences for modeling real-world phenomena. So, for example, right, we might have kind of a ball, in physics, it's falling towards the ground. We can measure its distance from the ground as a variable x. We can measure its velocity as v. And then we can write down a system of differential equations that describes the motion of the ball. Okay, these are standard equations, right? The rate of change of the position over time is v, and the rate of change of the velocity over time is minus g, where g is the acceleration due to gravity. Okay, and from physics or from basic calculus, we know how to solve these differential equations for the explicit form solutions. These are just the motion equations. And from these equations, we can deduce properties of the ball's motion, like when is it going to hit the ground, or how fast is it going to hit the ground, right? But here's another differential equation, this time from biology. It's modeling some process called glycolysis. It's a very simple model, but even for this very simple model, as far as I know, no one knows the closed form solution, or maybe there just doesn't exist a closed form solution. Okay, so the question is, well, how can we now deduce properties about this model if we cannot even find the closed form solution? Okay, and one fundamental idea due to Poincare, his picture is here, okay, is that we can view ordinary differential equations as so-called dynamical systems. These are systems that evolve over time. The state evolves over time according to some kind of evolution rule. Okay, and under this view, we can deduce certain kinds of qualitative properties of the system directly using the differential equations. Okay, and for this talk, I'm going to be focusing on planar dynamical systems or planar differential equations. And in this case, this idea has a pretty nice geometrical view. Okay, so what I've done here is I've plotted the so-called vector field associated with the differential equation. What that means is at each point, I've kind of drawn a vector corresponding to the right-hand side of the differential equation evaluated at that point. And what it means to view this as a dynamical system is to imagine just putting a point, say, over here, right, and having it flow according to those arrows. Okay, and in this particular case, what happens if you do that is, well, this point is going to kind of flow around here and come back onto its, flow around this loop. Okay, and what you can deduce about the solution from this picture is that, well, the solution of the differential equation from this initial state, right, is going to exhibit some kind of periodic behavior. It's going to start here, it's going to loop around, come back here, and then go around over and over again. Okay, so, and you can do the same thing from some other points, like the blue ones, okay? And again, you can draw the trajectories of those points. And for the blue points, you can see kind of from the picture that they start spiraling towards the red periodic orbit, okay? And if you're a biologist or a mathematical biologist, you might be quite excited because that means that this model of glycolysis exhibits some kind of limiting periodic behavior. And in particular, that kind of lines up with real-world glycolysis behavior where you observe certain kinds of oscillations. Okay, so perhaps this model can be useful for predicting, certain properties of the real-world glycolysis process. Okay, but if you're a person interested in formalized mathematics, then maybe not Poincare, but you might be interested in, well, how do we know that this visualization that I showed you here is actually the truth, right? I just plotted this in Mathematica, so so the subject of this work is the theorem due to Poincare and Bendixson. It's called the Poincare-Bendixson theorem, which says that under mild assumptions, trajectories of planar dynamical systems, basically this is the norm for those systems. Okay, and in particular, this theorem is actually not true in higher dimensions. It's only true on the plane. Okay, and this is in our paper and formalization. Actually, we have a more general version of the theorem. But for this talk, actually, I'm not going to focus in on the formalization. Again, I'm just going to work with the sort of the high-level description. And I want to talk about the challenges that we face in kind of formalizing this theorem. Okay, and our claim is that these challenges, of course, the Poincare-Bendixson theorem itself is, has nice applications, but our claim is that these challenges make it an interesting benchmark as well for formalized mathematics. Okay, and I have 4 challenges. And I'm going to start with so-called the 2 easy ones. Okay, and the first easy one is that it requires quite a bit of formalized mathematics background. Okay, so we kind of need the Jordan curve theorem. We need a library of real analysis, and we need a library for differential equations. In our case, we used Isabelle and the archive of formal proofs. Well, so we kind of meet all of these prerequisites. And the second challenge is, well, we kind of need all these dynamical systems concepts like the limit sets or periodic orbits. And for these, we kind of just formalize a new library in Isabelle, and that mostly follows textbook arguments. So that was also, well, not a huge challenge. Okay. Now the next 2 challenges are the ones that I want to focus on this talk. And the third one is, well, textbook proofs actually rely pretty heavily on sketches. Okay, and here's what I mean. Okay, so this is the proof in Chicone. Okay, the proof is an exercise. Draw a picture as a hint. Okay, and here's the picture. If you look at other textbooks, most other textbooks, you'll find something like this. Okay, it looks like some kind of spiral. Okay, and perhaps the proof of lemma 7.9 is just the picture. Okay, so of course, as far as I know, there's no proof assistant where you can put in a sketch and have it proof. So the question is, how can we formalize the sketch in a proof assistant? Okay, and kind of the fourth one is, well, rightfully so, right? Textbook proofs are going to argue by symmetry. They prove one of the cases, and then the rest of them are by symmetry. So how can we formalize these symmetries in a nice way so that we minimize copy and pasting of proofs? Okay, so I'm going to answer these 2 challenges. I'm going to show you our answers to these 2 challenges for one particular lemma that's used in the proof. Okay, and that's the Monotonously Lemma. And so that's the statement of the lemma, but I'll explain it to you as I talk you through the textbook proof, because I think it's quite intuitive. Okay, but I just need a quick definition, which is that of a transversal segment. And what this is kind of a line segment in 2 dimensions, because where the differential equation kind of points in the same direction, in this case, somewhat upwards, everywhere along the segment. Okay, and we'll use this in a bit. Okay, so here's the proof, and I'll explain the lemma as well. Okay, so suppose you start from this point, okay, and you kind of follow the differential equation and trace out this trajectory in blue. Okay, and in particular, your trajectory intersects the segment at 2 points, x1 and x2, right? Intersects at x1 and comes around and intersects again at x2. Okay. Now, what you can do is you can construct in 2 dimensions. What you can do is you can construct a Jordan curve. Okay, and that's this dashed green curve over here. And what the Jordan curve theorem says is this curve splits the plane into an inside and an outside. And the key property of this is that you kind of, if you follow a path from the inside to the outside, you must cross the Jordan curve at some point. Okay, and if you think about it, this is not going to be true in higher dimensions, which is the reason why this is the theorem that only holds on the plane. Okay, and of course we use the existing formalization of the Jordan curve theorem in Isabelle. So now what does the lemma actually say? Well, it says that if I continue following the trajectory from x2, okay, and if I intersect the transversal again, the only thing that can happen is it must intersect it at some point x3, which is further along from x1 compared to x2. So the 3 points must be ordered in this fashion along the transversal. Okay, and why is that? Well, these two situations are kind of impossible by construction. You cannot come out this way because these things are transversal, so you can only flow this way, and you cannot cross kind of cross the curve itself because of uniqueness theorem for differential equations. Okay, so actually that's almost the proof, but what I've shown you is only this case on the left. After you construct a Jordan curve, there's actually another case on the right, which is kind of symmetric, but you can see here you're kind of trapped inside in the shaded region, and here you're going to be trapped outside. Okay, and the other thing that you actually need in a full statement of the lemma is, well, I showed you what happens after x2. We also need to know what happens before x1. Okay, so a similar kind of monotonicity property is true before x1 as well. Okay, so that's the textbook proof of the lemma. Notice I used these sketches as well. Now we can try and formalize this theorem. And the formalization essentially follows what I told you, constructs the Jordan curve, and then we get stuck. And the reason we get stuck is because of these sketches. And the thing that we found was kind of implicit in these sketches is kind of a claim that these are actually the only two things that can occur. Okay, and if you just sketched on pen and paper, it's really hard to see what other cases can occur. Okay, so the thing is, if you look through the formalization itself, well, you actually notice that so there are two cases. In either of these cases, we are going to need three pieces of information about how the flow behaves. Okay, the precise details of what these information says is not super important. So, for example, in the left case, we kind of need to know that the flow goes from the outside sort of towards the inside, and in the right case, we kind of need to know that it goes from the inside to the outside. Okay, and we can actually prove that case split for the left and the right sort of quite easily. But the problem is now if we try to look at the second piece of information, we again get a kind of case split between the two kind of properties. And if you look at the third piece of information, we again get another case split. So and the problem is now instead of just two cases, we have 8 cases to deal with. And actually 6 of these cases are impossible. Well, if you just look at a sketch, it's impossible, but it's unclear how to actually prove that they are impossible. Okay, so in our paper, we essentially describe a new construction that allows us to prove that only these two cases are possible so that we can directly do this case split. We construct what we call flow regions, R1 and R2, which we can prove that they lie on opposite sides of the Jordan curve. And then we can split on whether one is inside or one is outside, for example. Okay, so that's kind of the high-level idea of how we dealt with the third challenge. Now, the other challenge I mentioned was, well, how can we formalize symmetry nicely? Okay, and of course you can add as many quantifiers as you need to the theorem statement. Okay? But what we actually did was we made use of Isabelle's locale system, and here's a high-level idea of how that works. So we're going to work in a differential equation locale, right, for the differential equation f. And then we might prove the lemma that I just told you about, okay, in about 760 lines. Okay? And now what the locale system gives us for free is we get a theorem about this kind of minus f, which is the reversed differential equation. And this is automatically generated because we have set up the sublocale relationship. Well, we have set up a sublocale, okay? And now the idea is we're gonna take this theorem that's automatically generated, and we can export it and apply some pre-proof rewrites, okay, that relate these two equations. And this maybe takes about 30 lines of boilerplate code. And what we now get is a symmetric lemma, okay, the symmetric version of this lemma for kind of the reverse time, okay? And that's how we formalized so-called symmetry in this work. And of course, that applies not just to this particular lemma. We used it basically throughout the formalization. Okay, so So I want to wrap up with some conclusions. So our claim was that the theorem is interesting benchmark for formalizing mathematics. We give the first, as far as we know, with a star, rigorous argument that we were able to formalize. And we use the located system to formally argue for the symmetrical cases. And here's the star. Okay, so while preparing these slides, we came across a proof in a book by Jane Cronin. And it's based on indexes, and I think some of you have started reading this, but here's a quote from the book. I'm just going to read it. Well, part of the difficulty in proving the theorem, the Poincare-Bendixson theorem, lies in the fact that considerations take place in the Euclidean plane, and distinguishing between intuitive and rigorous arguments in the plane is sometimes difficult. Okay, so we have not managed to try and formalize her proof yet, but at least she agrees with us that maybe there's a difference between the intuitive sketch and the rigorous argument. So a question that maybe I want to leave to people interested in formalizing mathematics, right? Our proof is actually pretty different from what you see in a textbook sketch. So is there a way to avoid that? Is there a way to formalize the sketch that would quite more closely follow what's in the textbooks? And in terms of future directions, the Poincare-Bendixson theorem is one tool that's useful for analyzing planar dynamical systems. There are many others like Lennard's theorem or Dulac's criterion. It would be nice to formalize them. Perhaps we can develop a library of reasoning techniques for example, doing these geometric arguments in the plane. And in the second direction, perhaps, is that the Poincare-Bendixson theorem itself actually generalizes beyond the Euclidean plane. It actually works on a sphere. It works on certain kinds of two manifolds. So it'd be interesting to look at what generalizations are possible inside Isabelle, for example. Thank you.
Thank you. So we have plenty of time for questions.
I have a question about, well, you mentioned that your proof is quite different from the sketches in the textbooks. What would be the difficulty with formalizing the notion of a sketch? I mean, other than coming up with it. Is the problem coming up with the formalization or actually writing it in a theorem prover?
Well, as I said, as far as I know, a sketch is just a picture you draw on a piece of paper, right? It's not some text that you can put into a proof assistant, and so, you kind of have to write it down as text, and that makes it not a sketch anymore. And also, kind of the argument that underlies the sketch, I would say is quite different from the construction we use, which kind of indirectly implies the information that we need for the cases. Thank you.
More questions?
Hey, so do you have plans to work in higher dimensions? I feel like this style of argument could somehow be transferred to flows through like cutting planes in a three-dimensional dynamical system. There are obviously lots of other challenges because dynamical systems are far more complicated in 3 dimensions, or can be, but it seems like some of these techniques at least could transfer over. And I wonder how much I'm sure you've tried to think about this, and I'm just curious what your thoughts are.
Well, so actually, this theorem itself, it actually doesn't hold in higher dimensions, but there are plenty of other theorems, like analogs that would hold. I've read pen and paper proofs, but I haven't thought about formalizing them, actually. So I'm not too sure about the potential for formalizing that. I'm actually perhaps more interested in there are other ODE theorems that do hold, for higher dimensions, and I would be interested in formalizing those, for example. Thanks for the question.
More questions? I have a question. Did you just do this for the fun of it, or was there a motivation from the analysis of hybrid systems?
So I actually wanted to learn Isabelle. This is my sort of my first proof in Isabelle. So and I was really interested in the Poincare-Bendixson theorem because I think the proof is nice. So I worked on that. But there are other things that I have formalized that I have for more hybrid systems verification perspective.
Okay. Right. Well, I think we've come to the end of this talk. Let's thank the speaker again.